Okay, great. Yeah, welcome everyone. Good morning. So today we have Prashant Nalini Vasudevan, who's an assistant professor at Department of Computer Science at the National University of Singapore. He works in cryptography, but broadly an intersection of areas with complexity theory and generally a lot of interesting problems in theoretical CS. So prior to this, he did his postdoc at UC Berkeley. And even before that, he completed his PhD with Vinod from MIT. It is a great pleasure to have you here. Tell us more about your work on batch proofs, are statistically hiding. Take it away, Prashant. Yeah, thank you so much for agreeing to give this talk.
Yeah, of course. Thanks a lot for having me. So this is about our work from a couple of years ago, maybe a year and a half ago now, called Batch Proofs of Statistically Hiding. This was with Neer, who is at NYU now, Chetan, who's there, who's in the meeting, Omar, who's at Tel Aviv, and Ron, who is at the Technion. So this, the title of the paper as well is Batch Proofs of Statistically Hiding. And there are a couple of different perspectives one can take to the results in the paper. And the one I'm going to take today is perhaps better stated in these terms, which is as an attempt to answer this question. Okay, I'll explain all of these. An attempt to answer this question is the perspective I want to take in this talk of the question of when can you batch proofs. So what do I mean? What do I mean by batching proofs? Well, a batch proof, okay? A batch proof is a kind of interactive proof. So I'm going to define it throughout this talk and in the paper as well for NP languages. So it's an interactive proof for some NP language L. It's a batch proof if it satisfies all of these conditions. Okay, the setup is that it takes many instances as input, both the prover and the verifier. They get these T instances of the language, and the prover has as private input witnesses, purported witnesses for each of these instances. And then they interact as in a normal interactive proof, at the end of which the verifier either accepts or rejects. And what I want this to be is I want this protocol, this interactive protocol, to constitute a proof that all of the instances that were given are contained in the language. That all of the xi's are in the language, right? So I'm going to require the following properties from this. I'm going to require that both the prover and the verifier are polynomial time algorithms. Of course, it's still non-trivial because the prover has these secret witnesses, right? Without that, it perhaps isn't meaningful to say both of them are polynomial time, but the prover has access to these witnesses. So I can ask for both of them to be efficient. And I'm going to ask for completeness and soundness properties as usual, except that for completeness has to capture the fact that all of the instances are yes instances. And because the prover is efficient as well, I'm going to be a bit more restricted in my, I'm going to be a bit more, what do you call it? A bit more relaxed actually in my definition of completeness. I'm going to say if all of the inputs are in the language and all of the witnesses the prover was given were valid witnesses for the corresponding instances, then at the end of the protocol, the verifier accepts. Okay. On the other hand, soundness says that if there is even one instance among these, then no prover, not even an inefficient prover, can make the verifier accept. Okay, no prover strategy, even if it is inefficient, can make the verifier accept. Right. Notice that these two are not, completeness and soundness as defined here are not exhaustive. Meaning there are, for example, if all of the x1 to xt are yes instances, but the witnesses the prover has are not valid, then these properties say nothing about what the behavior of the protocol needs to be, and we'll just ignore those possibilities. Right? All I care about are these two properties of completeness and soundness. And in addition, I'm going to ask for a property about how much interaction happens in the protocol. Right? There is, and I'll refer to this property as succinctness, and I will place a limit on the amount of communication in the protocol itself. Right? Because without this, notice that this is trivial, right? Because a prover can always just send all the witnesses to the verifier, and that is a valid proof that all of the instances, if they are in the language and the prover has the witnesses, it can do that. That satisfies completeness. And if they are not in the language, then because it's an NP language, the prover cannot find bad witnesses that will make the verifier accept. So if I do not place this bound on this communication, then this is a trivial thing to do. You can just send everything. And even more generally, if I if I don't place, you can ask the same question. Also, if I do not place this constraints on efficiency on the prover, right? Then you can ask, okay, what languages can you have this for? And in that case, you can actually show that batch proofs like that, if you don't have restrictions on the honest prover's running time, you can actually get it for any language that has an interactive proof. By connections to the IP equals P space, you can even satisfy the succinctness property really well. And you can get this for a huge class of languages. But I'm going to restrict myself to asking about polynomial time provers, right? And then the question only makes sense for NP languages because otherwise you may not even have polynomial time provers. And then I want to ask, okay, within NP languages, which languages have these proofs that also have the succinctness property? And proofs like this, interactive proofs like this, are what I will refer to as batch proofs. Proofs that have the succinctness property, I call batch proofs. All right. And one thing to pay attention to here is that the amount of communication I'm allowing is very, very small. It's not even 1 bit per instance. Right? The same questions that I'm going to ask now will still make sense even if you relax this a little bit. Because again, the naive protocol of sending all the witnesses takes communication something like t times the size of each witness, right? You can ask, can you get a protocol where the communication is maybe t times square root n or something, where n is the size of the instance. So even that is a non-trivial question. But for today, we'll restrict ourselves to the even more extreme definition of succinctness, where we'll say you don't even have 1 bit of communication per instance. Okay. And by the way, feel free to stop me anytime if you have any questions. I cannot see the chat or anything, so somebody will have to speak up and interrupt me if you have any questions.
Yeah, I can take a look at the chat. Don't worry.
Okay, thanks. Yeah, so this is the definition. This is what a batch proof is. Okay, this is what I will be calling a batch proof at least. And the question that I want to and also another thing is that the most meaningful regime to think about is when T is very, very large. Imagine T is much larger than each instance and each witness. Okay, that's when it's easiest to interpret whatever I'm going to say. Otherwise, also it is meaningful, but it's not as easy to interpret perhaps. So imagine T to be some very large polynomial in the input length. Yeah. So the question I want to ask here that we started out asking really that motivated everything we did here is this question: is the question of which languages in NP have batch proofs? Okay, and this is perhaps a purely complexity theoretic question, right? Because I have defined this new kind of proof system, and I'm asking which languages have these proof systems. Very purely complexity theoretic question. As we'll see later, I'll tell you as we'll get to eventually. This also has some implications for cryptography and so on. But we'll put that off till later. I'll talk more about that later. But for now, we are interested in just this purely complexity theoretic question of which languages in NP, again, because it's the way I have set this up, it's only defined for languages in NP. So which languages have these batch proofs? Right? That's the question. And it was, this was actually answers to this question, meaningful, non-trivial answers to this question only started coming out in the past decade also, when there was this line of work by Reingold, Rodblum, and Rodblum, who showed that over like 2 or 3 papers, they showed that any language in NP that has an unambiguous NP relation, meaning that there is some relation, some NP relation for this language for which there are unique witness. For every S instance, there's a unique witness that proves that it's a S instance. Like think about, for example, something like factoring, right? Where for any number has like a unique prime factorization, something like that. So if languages of this form, they showed that you can actually get batch proofs for them. You can take T instances of such a language and come up with an interactive proof where the communication is much smaller than T. Of course, you can always have these for languages in P, right? For languages in P are trivial because the verifier can just do all the work. There does not be any communication. But outside of that, this was pretty much the only systematic result that showed that if you have this particular property, then you have this batch proof, right? And apart from this, we also know some specific examples of structured languages, some specific languages that have these batch proofs. As an example, maybe you can think of things like quadratic religiosity and all, where because of some kind of algebraic structure in the language, you can combine multiple instances in some clever ways to prove things about many instances simultaneously. Right? So we have some examples like that perhaps are not in UP. But this is pretty much all we knew. right? So within NP, the question was for all languages in NP, and we knew that for languages in UP, you could get these proofs. And for some isolated languages outside this class, we knew you could get this. But that's pretty much all we knew. That's pretty much all we know. Even today, actually, this is pretty much all we know about. If you're asking what languages I have batch proofs for, the only constructions I know are pretty much this. Right? And this leaves many questions. I know many questions open. In particular, we don't even know what to say about the possibility of these batch proofs for even the hardest languages in NP. Like take SAT, for example, right? Can you have these kinds of batch proofs for SAT? We do not know. And what we tried to do is we tried to see whether there was any reason that SAT should not have these proofs, because at least our intuition was that it should not have these proofs. It was not a very strong intuition, but we felt that SAT was unstructured enough that it perhaps it does not have these proofs. And then we asked, okay, can you justify this? Is there any reason to actually believe this? And what I'm going to tell you about today is one reason for perhaps believing that SAT is not going to have these proofs, or NP hard languages are not going to have batch proofs. Right? Again, it's not a very strong reason. It's not very strong evidence, but it's some evidence, and it also brings up some interesting connections that maybe hopefully in the future will be developed into either stronger reasons to believe one way or the other, or to construct other interesting things. Okay? So the partial answer to this that we have, at least the approach to answering this question that we have, is the following. So what we show is that if your language has a batch proof, then it also has some other property, right? And if this other property is something that you do not expect SAT to have, for example, then you would expect SAT does not have batch proofs, right? And the specific property that we show is that if your language has a batch proof, then it also has a different kind of interactive proof that is called an SWI proof. And the star and everything, all of this I'm going to define in a moment. But this is going to be our approach. Okay. So what is this SWI star proof? Well, the WI there stands for witness indistinguishability. Right. It's again a property of an interactive proof system or a non-interactive proof system. And it's defined as follows. So, and you can think of it as like a weaker version of zero knowledge. In some senses, it is. And the property is actually very simple to define. So imagine you have again some language L, okay, some NP language L, and there is an instance X of the language that say has two witnesses, W0 and W1. It could have many, but pick any two of those. And what I'd like, so an interactive proof system for the language L, it has to have the completeness and soundness properties. But beyond that, it has to have the following property. Okay, and the property I want is, so the language has an efficient prover that is given a witness, and then the interaction happens, right? So imagine in one situation, in one case, the prover is given the witness W0, and the interaction happens with this instance X, with the verifier, and then at the end, verifier outputs whatever. And in another case, the prover is instead given W1. Right? And what I want is that in these two cases, the view of the verifier looks the same. Right? And this has to be true even if the verifier doesn't run according to the protocol specification. Even if the verifier is actively trying to deviate from the protocol to try to figure out whether the prover is using W0 or W1, it should not be able to figure it out. Right? This is the property of witness indistinguishable. And you can see why it has the name, because it's indistinguishable which witness the prover is using. And that's why it's called witness indistinguishability. And we will specifically be concerned with statistical witness indistinguishability, which is a very strong way of formalizing this, where we say that irrespective of how the verifier behaves for any instance in the language and any pair of witnesses, the views of the verifier in the two cases are statistically indistinguishable. A weaker version is to say that they are computationally indistinguishable, and that's a weaker version of saying it, but we will be talking about statistical witness indistinguishability. Right? So note that I still only allow polynomial time verifiers here. The V star is, I'm still asserting it to be polynomial time, but the view is statistically indistinguishable. Right? And I will refer to and this notation is basically saying that if you look at these two views, and the view is essentially the randomness of the verifier together with all the messages it sees in the course of the protocol. And what the statement is saying, the way to interpret it is that if you look at the distribution of the views in the two cases, the statistical distance between them is at most some epsilon. Okay, and I'll be using the total variation distance for the distance between distributions here, and the bound on this distance I'll be referring to as the witness indistinguishability error, right? Just like you have completeness and soundness errors. And I'll also be talking about a weaker condition called honest verifier SWA, where instead of asking for this property to hold for every V star, I'll only ask it to hold for the honest verifier V star, where the verifier does not deviate from the protocol, and at the end you want this property of the views, right? And yeah, one observation here is that this property is trivial to get if you allow the honest prover to be inefficient. Because you can just look for, given the instance, you can just look for some canonical, you can ignore the witness you're given and look for some canonical witness and just use that every time in the proof, right? So if the prover is inefficient, then it doesn't even make sense. This is vacuous, this property can be vacuously achieved. So again, we are only going to be talking about efficient provers here. Any questions about this so far? About any of the definitions?
So, Prashant, I had a immediate, maybe very simple question, but how does this modified statistical witness indistinguishability compare with the computational one? So you have PPT verifier still.
Yeah.
So does this
The difference
how does
is that
it
in the computational version, you want the views to be computationally indistinguishable.
correct? Like, is there is that would still be weaker definition than this, right? Like, is it
Yeah,
very
yeah,
clear?
it is still a weaker definition than this. Yeah.
Okay.
Right. So to go back to the previous slide, to expand on what I was saying there, what we show is that if a language has a batch proof, then the language also has an honest verifier SWA proof. Okay, and further, with a couple of caveats, and this was the start back then, back in the other slide, a couple of caveats. In the protocol that we get, so we take a batch protocol for batch proof for L, and we construct an honest verifier SWA proof protocol for L. And in the protocol that we end up constructing, you end up having a non-uniform prover. And also the SWA error that we get, the distance between the views, we cannot quite get it to be negligible. Instead, we get some inverse polynomial SWA error. Okay, and these two would be pretty big issues if you're trying to use such a protocol, right? Because if all you had was a construction with non-uniform prover and you wanted to use this protocol, then where are you going to get the non-uniform prover from, right? All you know is that there exists some honest prover that works. So how are you going to get it? That's complicated. So you don't know how to get approval, so you can't use it. And similarly, if your error is only some 1 over polynomial, then there are some security concerns with that, right? So if you try to use this protocol somewhere, and again, you might try to use this protocol because this witness indistinguishability is a cryptographic property, right? And it does have uses in protocols. So you may want to use such a protocol, but then there are these issues. So you can't actually use the protocol that we get out of this thing. On the other hand, if all you're interested in is trying to understand the complexity of batch proofs, then these two caveats, they don't make that much of a difference because they don't make a qualitative difference to the set of languages that you believe have such proofs. Like if you think of the set of languages that have SWA proofs with uniform provers and negligible SWA error, and the set of languages which have SWA proofs with non-uniform provers and 1 over poly SWA error, then there's no real reason to believe that these are very different. Right? Maybe you can construct some pathological language that has one but not the other, but at least in the sense of getting a qualitative idea of what kinds of languages have these proofs, these two don't matter as much. So if the question you're trying to answer is what languages should I believe have batch proofs, then one of these is as good as the other. Right? So we do this, and then you can also take this a bit further. You can show that if the batch proof you started with happens to be public coin, meaning that all of the messages of the verifier are just random strings. Right? It just samples a uniformly random string, sends it to the prover every time. Right? At the end, it may do arbitrary things, but otherwise the verifier just sends random strings in all of its messages. If your batch proof is like that, and a lot of interesting proof systems are like that, maybe not batch proof systems, but interesting proof systems in general. So then the public coin, then the honest verifier SWA proof you get remains public coin, and then you can use some well-known transformations between these kinds of proofs to make the to modify the protocol in such a way that it also works for any verifier. It doesn't, it works, you can get a general SWA proof for the language. It doesn't have to be honest verifier.
Prashant,
While
there's a
maintaining the
question
same.
in the chat. There's a
Uh,
question in chat. So Siva was asking if perfect statistical CKB guarantees such witness indistinguishability.
if perfect, what? Second?
Perfect or statistical zero knowledge proofs guarantee such a witness
Oh yeah,
indistinguishability.
yeah. So they would because, and in fact, that's an even stronger guarantee than zero knowledge is strong. I can't say strictly stronger because they could all end up being the same, but it is a stronger guarantee. Witness indistinguishability is implied by zero knowledge. Perfect or statistical zero knowledge would imply statistical witness indistinguishability, and computational zero knowledge would imply computational witness indistinguishability. Yeah, right. So this is what we show. Any other questions?
I think
Okay.
nothing so far. Yeah, go
Uh,
ahead.
Okay, so this is one of the things we show, okay? And what I'm going to do in the rest of the talk is I'm going to show you how we show this. And the idea is somewhat simple. Like we should be able to go through all the main ideas in not too much time. And then I'll tell you a little bit about how you can use both this result and the ideas in the proof to do other things, to come up with constructions for computationally sound batch proofs, for example, which we have constructions from. I'll tell you more about that. And also how you can get rid of the non-uniformity of the prover and make the protocols actually useful in some cases. All right. So yeah, this was just the contrapositive of what I was writing earlier. So yeah, so before I go to the techniques, so just to recap, just to talk about these SWA proofs, right? So we started out with asking what languages have batch proofs. We reduced it to the question of what languages have SWA proofs. And so to just quickly tell you what we know about this, well, the class of languages which have unique witnesses vacuously have such proofs because the definition is vacuously satisfied. And because if there's only one witness, then it's vacuously you cannot distinguish between with one witness and another witness that the prover is using because there's just one witness, right? So UP is languages trivially have these proofs, which is consistent with what we saw earlier, that UP languages have these batch proofs as well. And yeah, going back to the question that was just asked, you can also show that languages that are in SEK intersect NP have such proofs. And the intersect NP is important here because, as I said, the zero knowledge property does imply the witness indistinguishability property. Uh, but whereas zero knowledge makes sense for languages that may not be in NP, as I was pointing out earlier, your witness indistinguishability only makes sense for languages in NP. Otherwise, it's not even defined, right? So you can only really ask the question of does this language have a witness indistinguishable proof if the language is already in NP. So if you were asking about does a zero knowledge proof imply a WI proof, then you can only ask that about languages that are in NP. So if you think about statistical zero knowledge, you would be thinking about languages that have statistical zero knowledge proofs that are in NP. Right? And then you can ask, okay, if a language is an SDK intersect NP, does it have an SWA proof? And this is actually not very immediate because the fact that a language is an SDK and a language is an NP does not necessarily mean that it has an SDK protocol where the prover is efficient given a witness, right? Because that is what you want in the SWA proof. To get an SWA proof system, you want an efficient prover that is efficient given the witness, right? And the fact that a language is an SDK intersect NP does not mean that it necessarily has an SDK protocol where the prover is efficient. At least it does not immediately seem to be the case, but people have shown after a lot of work, people have shown that this is in fact true, that a language that is an SDK intersect NP does have an SDK protocol where the prover is efficient given the witness. Okay, and this was a series of works done maybe about 20 years ago now. Not sure exactly what the timeline was, but I can find you references. Anybody who's more interested in these things, just send me an email and I'm happy to give you references for all of this. You can also look at the paper. It should have all the references. Right. So these two classes of languages have SWA proofs. Right. Um, and you can also take some simple combinations of these languages. Like you can take one language from UP, one language in SEK intersect NP, and combine them. You could take like the OR of them or something. Like some combinations continue to have very simple SWA proofs that you can derive from the proofs for both of the languages, right? But still, this doesn't say much about NP-hard languages. We don't really understand which languages have these SWA proofs. This has not been studied that much, nearly as much as SDK proofs, for example. So in particular, we don't have very strong beliefs about whether SAT has these, for example. If SAT happens to have SWA proofs, it's not clear that it will contradict anything else that we believe. Even though to me it seems very unlikely because SAT is so unstructured, but stranger things have happened. So it maybe it does have these things, but so far it's not clear that whether it does or does not. And another thing to point out here is whereas for UP we do know these batch proofs, right? For SDK intersect NP we do not know. For SDK intersect UP, we do know because UP has all of these, but for SDK intersect NP, which is a larger class, we don't know batch proofs yet. Okay. Yes. So with that said, I'm going to tell you now about how a proof works, how a construction works. And I'm going to do this by taking the simplest possible case. Okay, like in general, we want to talk about. In general, we want to talk about these languages that have interactive proofs, interactive batch proofs. But let's start with the simplest kind of batch proof, where you have the prover and the verifier. The prover has all the witnesses, and imagine the entire proof has the following structure. Okay, there's some function that the prover computes of the instances and the witnesses it has, and it uses this to compute the some proof string pi, and it sends pi to the verifier, who decides to accept or reject. Okay, like this is the simplest kind of proof system you can have. And in fact, if you don't have restrictions on the size of the pi, you can get such a proof system for NP languages, right? Where you can just send all the witnesses, but you can't do that because pi has to be short. And by our setup, the prover has to do this function f has to be computable in polynomial time. Right? And I'm going to make one further simplifying assumption that the function f that is being computed by the prover is also deterministic. Right? In general, this does not have to be the case, but for now, pretend that it's deterministic. Right? And the condition that we are imposing on this is that the length of the output of this function is smaller than t to the 1 minus epsilon. Okay, so what I want to do is I want to start with a language that has a proof system like this, that is complete and sound according to the definitions I listed in the beginning. And I want to use such a proof system to construct a different proof system for the language that is an SWA proof system. Okay, so this protocol is proving that x1 up to xt, like these t instances are all in the language, and it's succinct. I want another proof system that doesn't have to be succinct or anything. It's given one instance. It has to prove that that instance is in the language, but it has to do it in a witness indistinguishable manner. And this is my objective now. This is what I have to do. And the approach I'm going to take to this, the observation that really enables the whole thing is the following observation, that because so you have t instances that is known to both the prover and the verifier, but then you have these t witnesses that's only known to the prover, and the prover is sending something, this string pi, the prover is sending to the verifier, right? But the pi is shorter than t. It has fewer than t bits. So it cannot possibly remember all the information that was there in all the witnesses. Right? It has to be losing some information somewhere. Right? And that is the basis of our entire argument. Right? So, and what we will do to take advantage of this is, so in the SWA, in the attempted construction of the SWA proof system, the prover is given some xw, right? The verifier is given this x, the prover is given some x and w, which is the witness for the x. And it wants to prove that to the verifier that x is in the language while hiding information about x, hiding information about w, right? And our observation about the batch proof system is that this pi, simply because it's shorter than the number of witnesses, has to be losing information about some of the w's. It may be remembering some of the w's really well, like maybe the first witness is always part of pi, right? It could be remembering some of the w's, but it has to be losing information about a significant fraction of the W's. Right? Otherwise, it cannot be this short. Right? So what we will do to take advantage of this is, given this X and this W, we will hide this W among all the WIs that were in the batch protocol. Okay. So what we'll do is something like this. So the prover has the W, the verifier and prover both have the X. We have the access to this batch prover, right? And this prover needs needs T instances of witnesses. So what we'll do is we'll pick, imagine for now that we can do this. Okay, we'll see how we can do this later. Our approach will be to try to pick some instance witness pairs that are in the NP relation for the language. So you pick many XIs and WAs as that XI is in the language and WA is a witness, as a valid witness for XI. And then you pick a random location from 1 to T, and you take the actual instance witness pair you have and put it in the jth location, and then compute the proof as before. Do whatever the batch prover was doing. Compute this proof pi and send the pi to the verifier along with information on what the instances you picked were and the location in which you put the X. Right? And then the verifier will simply run the batch protocol's verifier with the instance that the prover told it about. The prover said, I picked x1 to xt and I put the x in the jth location. The verifier will say, okay, I will construct that instance where I have x1 to xt and xs in the jth location. And then take the proof pi that the prover sent it and think of this as the batch protocol's proof string, and then it just runs the verifier from that. Right, and this is the entire protocol. This is what the protocol is going to look like. Okay, and it's clear that the completeness and soundness should be clear, because if X is in the language, I am picking all of my x1 to xt to be in the language with valid witnesses. Okay, I haven't told you how to do it, but that's what we're doing. So if X is in the language and W is a valid witness for it, then it satisfies the hypothesis for the completeness condition of the batch protocol. So the verifier will accept with high probability it is. And if X is not in the language, then it satisfies the hypothesis for the soundness condition in the original definition. So the verifier will not accept. The batch verifier will not accept. Right? So completeness and soundness are easy to get from here. And what remains to argue is that this protocol, it's not fully specified yet, but we want to get witness indistinguishability and along the way figure out how to pick these Xis and Ws. And that's what we're going to do. Any questions about what this protocol so far? Okay. Remember that the view of the verifier here is the proof pi that was produced along with the instances that the prover generated on its own and the location of where the X was planted. That's the entire view. Right. Right. So we want to now fill in the gaps in our protocol in such a way that this becomes witness indistinguishable. Right. So how are we going to do this? Well, let's start by again simplifying the situation considerably. Let's say that to get witness indistinguishability, the property states that for any instance and any pair of witnesses, you have the indistinguishability property, right? But let's take one specific instance and a pair of witnesses for it. Like fix some particular X that is in the language and two specific witnesses, distinct witnesses, W0, W1 of this instance X, okay? And let's try to get witness indistinguishability for just this instance and this pair of witnesses, right? And now I want to ask, is there a way that you can pick the other instances and witnesses so that the proof looks the same, irrespective of whether the witness W0 was given to the prover and W1 was given to the prover. Right? This is what witness indistinguishability comes down to. I want to pick X1 W1 up to X2 XT WT in such a way that these two look the same. It doesn't matter whether I use XW0 or XW1, the output of the F, the string pi, should look the same. Right? And here it's there's perhaps just one choice, that one obvious way to do this, which does work, which is you can pick all of the Xis to be equal to this X, because we fix this X, right? We don't care about how the protocol behaves on any other X. We only care about this one particular X and these two witnesses. So in the protocol, you can say I will pick all of the other X1 to Xt to also be equal to X. And the corresponding witnesses W1 up to WT, I will just pick them to be random from W0 and W1. And if you do this, then imagine what the input to the F looks like. It's a bunch of x comma W0 or x comma W1, where W0 or W1 are picked at random. And then you have this x comma W, which is either x comma W0 or x comma W1. But it's just one out of t such instances, right? So having just one of them being fixed to W0 or W1 should not affect the distribution of the things too much. That's the reason, that's the intuition here. Yeah, we are hoping that there's so much sort of chaos, so much noise in this system that fixing one of the tuples to one or the other doesn't really matter. Right? And to do this properly, we are going to appeal to this one lemma that formalizes pretty much what I just said. And this is a lemma that was shown by Andrew Drucker and then simplified by Holger Dell in a series of works that I'll be talking about in a bit, actually, in a few minutes. So, and the lemma is the following, all right? It says that the property that we want actually holds for any compressing function. So they say you take any function, any Boolean function, not Boolean, any function that takes t bits of input and outputs some row times t bits of output, right? So for some row that is smaller than one, it could be a constant or something that goes to 0 or whatever. So take any function that looks like this. What they say is that if you look at this distribution where I take my G and apply it to this, apply it to some B1 up to BT, where all of the B1 to BT are uniformly random strings, except I pick a random location and set it to 0. And I also tell you what the location is. Okay, so I have this function that's shrinking. I pick a random location, random input coordinate. All the other inputs are random bits, but this one bit I fix it to 0. And I also tell you which bit I fix to 0. Right? So I either give you this or I do the same thing, but I fix that bit to 1. Right? And what this lemma says is that these two distributions are statistically close. Which again captures the property we were saying earlier, right? The property that if you have a function whose output is smaller than its input, then the output cannot possibly be remembering everything about the input. It has to be forgetting something. And here what we are saying is that it will be forgetting something with some probability. Like because we are picking this j at random, the bit that I'm fixing will be forgotten with some probability. That's what this lemma is capturing. Right? And you can even say what the distance between, you can even get good bounds on what the distance between these will be, and it will be like square root of rho, where rho is the shrinking parameter there. And this is also tight. You can also show it's tight. It's a nice exercise to show that this is tight. But this is what we have, right? And similar things have been used in the past in cryptography as well, with where these ideas have been used with things like PIR, where again you have this kind of lossiness property, because in PIR you have this big database that the server has, and you're communicating with the server, but the server's output is short. Server's messages are short. So again, it's losing some information about the database, and you can actually use this to get some security properties from this, from a PIR protocol. Right? So again, for similar reasons, similar lemmas have been used in the past, and this is what we'll be using. This is the core of our technical proof. Right? So we have this lemma. Now it's a simple matter of identifying the functions in our construction with these functions and then applying the lemma. Okay. So to prove that the construction above works for this one particular x and w0 w1, so we take your x w0 w1, and what our protocol was doing was exactly this. It was saying I'll set all the other xi's to the same x. I will pick all of the other witnesses at random from w0 w1. I'll pick a random location j, and I'll put my instance that I got at the location, right? So just to give these two more convenient names, I will refer to the proof string generated when the witness is w0 as pi0 and when it's w1 as pi1. Okay, and this is not fully determined. It's randomized because there is still some randomness that goes into the production of the string. So it's some random variable. That is, it's some distribution over strings. Right? So you have pi0 and pi b. And then if you just apply the lemma that I showed you with this function, the function that specifies which of the two witnesses is being used in each location. Right? If you just do that, and you can see the correspondence directly. So pi0 corresponds to exactly what you get when you pick a random location j and set bj to 0. Right? That's exactly what pi 0 is. And if you set bj to 1, that's what pi 1 is. Right? And pi 0 and pi 1 are exactly the two things you want to be indistinguishable as well. And that's exactly what the lemma, that's exactly what the lemma gives you. It says that the distribution j comma g of etc. when you fix one of the bits at random to 0, and the distribution of j comma g of etc. when you fix the bit to 1 are close. That's exactly the verifier's views in the two cases. And this shows that the protocol that we described, if you pick the xis in this particular way, is witness indistinguishable for a specific a priori fixed input and pair of witnesses. And this is the first step of everything. So any questions so far? Okay. So we've done this, and I want to point out the next step is I want to point out that this actually holds not just for a single x and a w0 w1. This also holds for distributions over x w0 w1. So if you have a distribution over x w0 w1, and imagine all I want to get is I want to get witness indistinguishability with high probability over this distribution. Like maybe there will be some x w0 w1 in the support of this distribution for which my protocol will not be witness indistinguishable. Okay, that's okay. As long as with some decent probability, my protocol is witness indistinguishable. So that's what I want here. I want random samples from this distribution. I want to have witness indistinguishability for random samples from this distribution, right? And a simple observation is that exactly the same thing we did with almost the same argument will work in this case as well. So in this case, the actual instance witness pairs are sampled like this, for which you want witness indistinguishability. And you can sample the xi's and wi's in this way, where you take the same distribution for any I, you take the same distribution, sample from it, and then set the x to be the xi that comes, or x that comes out of it, and set the wi to be one of the two witnesses that come out of the sample at random. Right? So the distribution, every time you try to sample from it, it gives you some w0w1. Set your xi to be the x and the witness to be one of the two at random. So you do this, and then again you do the same thing as before. You pick your xi's wi's like this, and you again plant your actual instance at a random location. Right? And again, you define this random variable for the proof string. And you can again use the same definition of the function. You can invoke the lemma that we have, and with some slightly more careful arguments this time, because the verifier's view actually consists of the x's and the xi's as well, right? So you have to be a bit more careful, but with a little bit of work, not particularly difficult work, you can show that the same thing holds, that these two distributions are statistically indistinguishable, which in effect says that the expected WI error is small and things like that. But this gives you this kind of average case witness indistinguishability. So this kind of distributional witness indistinguishability, as I would call it. And so you can define like you can define it in a couple of different ways. You can either define it as the expected witness indistinguishability error, and you can say that has to be small, or you can directly define the distribution of these two things as the distribution of the views for random instances, and say that has to be small. Right, both are sort of equivalent, but in the end, you get this. You get this kind of average case distributional version of WI for any distribution. Right? For any distribution D, it has to be sampleable because the prover has to be efficient, but ignoring those things, for now, for any distribution D, you can get witness indistinguishability by just filling in the xi's and wi's using the same distribution. Right? And from now on, and to summarize, this is what it looks. This is what we have so far, right? What we have said so far is for any distribution over instance and witness pairs, there is some distribution over the xi's wi's that I just described now, for which the proof is witness indistinguishable on average. Right? On average, the proof is witness indistinguishable. This is what I have. But remember, what I want is proper witness indistinguishability, right? And that says that for every input and witness pairs, I need to have witness indistinguishability. So this looks like this. I want to be able to fill in the xi's and wi's in one fixed way, where I have the way I'm doing this, it has to be sort of oblivious to, well, ideally it doesn't really have to be, but a sufficient condition is that if there is a way of picking the xi's and wi's in such a way that for any input and witness pairs, the proof system is witness indistinguishable. This is what I actually want, right? Because this is what the definition of witness indistinguishability says it has to hold for every instance in witness pairs. So I have this and I want this. And if you stare at this for a bit, you'll see that there's maybe a somewhat standard way of going from one to the other, which is to use a min-max based argument, right? Um, so let me say how this will go. So this is what I start with, this distributional witness indistinguishability. I want actual witness indistinguishability. To do this, I'm going to set up this game, okay? This two-player zero-sum game, and it has to be zero-sum for me to do what I want to do. Where there are two players. One player picks an input and a pair of witnesses, and another player picks all the xi's and wi's. And let's say it picks xi's and the wi0, wi1, and the wi is chosen as a random one of these two. Okay. And I define the payoff in my game to be the quantity I really care about, which is the statistical distance between the views of the verifier in the two cases. In the cases where between pi0 and pi1, as you see there, right? In one case, what happens? So given once p1 has picked these things, and p2 has picked these things, the way the game proceeds is first, for every I, you pick a random one of these two to keep as the wi, and then you put the x, you pick a random j, you put the x in the location, and you either use w0 or w1 as the witness, right? That's the two things on the left and the right of this payoff expression. And you take the statistical difference between these two distributions. Right? This is going to be the payoff of the game, given these two strategies. It's going to be the payoff corresponding to these two strategies. Right? And once I have set this game up, the rest of the argument is very simple. So what I showed you is essentially this, that for any mixed strategy of the player one, which is the same as saying for any distribution of x, w0, w1, that exists a mixed strategy of player two, which is to say there is some distribution over the xi, wi0, wi1, which in our construction is the same, right? Xi, wi0, wi1 is the same. The distribution is the same as the distribution of x, w0, w1. So for any mixed strategy of P1, there is some mixed strategy of P2 for which the expected payoff, the expectation being over all the random choices I just described, for which the expected payoff is small. Right? And also over the mixed strategies of the two players. Right? So this is what we have shown so far. And what we want is this on the right-hand side, where we want to say that there exists one mixed strategy of P2. There exists one way of picking the xi's and the wi's and so on. So that works for any pure strategy of P1, because a pure strategy of P1 is some x, w0, w1, right? So I want one mixed strategy of P2 that works for every pure strategy of P1. And works means that the expected payoff is small because I want the statistical distance to be small, right? And this is exactly what the min-max theorem, von Neumann's min-max theorem, says, that these two are equivalent. That if for every mixed strategy of P1 there exists a mixed strategy of P2 for which the payoff is bounded, for which the expected payoff is bounded, then there exists just one mixed strategy of P2 such that for any mixed strategy of P1, the expected payoff is small. But we don't care about mixed strategies of P1 anymore. We only care about pure strategies. So it's better than what we got. Actually, it's equivalent, but doesn't matter. Right? And so any questions about this? Right, and this is pretty much the entire proof. There are, of course, details to work out and things to define very carefully, but this is the entire proof. You show that for any distribution over instances, you can get this distributional witness indistinguishability. And then you use the min-max theorem to say that exists one way of choosing x's and wi's. You don't even have to look at the x and w0, w1 to do this. Such that works for every possible input and witness pairs. Right. Of course, one thing I have not addressed so far is the efficiency of the prover, because in the end, we want an efficient prover for our SWA protocol, right? And the min-max theorem does not tell you anything about efficiency, but there are some later versions of the min-max theorem that do give you some efficiency at the cost of non-uniformity. So there are ways to make the strategy of the conclusion of the min-max theorem is that there is a mixed strategy of P2, right? And that mixed strategy of P2 is what is going to give you the honest provers algorithm in the actual protocol. The min-max theorem on its own does not give you an efficiently sampleable mixed strategy of P2, an efficiently implementable mixed strategy. But you can, later sparse versions of the min-max theorem do give you this. They say that you can essentially just take the distribution, take the optimal mixed strategy for P2, and just take many, many samples from it. And then afterwards, you can just use the empirical distribution from those samples. And that will still give you some approximate bounds, but it will still give you good enough bounds. And you can use that, but the cost of doing that is, of course, the non-uniformity of the prover, because you have to remember the samples that you got in for the empirical distribution, right? And that has to come from somewhere, and we only know how to get it from non-uniformity. We don't know how to get it in some more efficient, uniform manner. Yeah, this is how you prove this. This is how you prove the theorem. Of course, there are details, of course, but this is pretty much the entire overall proof strategy, right? Oh, and it looks like I'm almost out of time. I didn't realize it would take this long. So let me go through the rest somewhat quickly. So everything I've said so far has been for this very non-interactive kind of batch proof, right? Where the prover just sends this one message, it's deterministic and so on. But it turns out that's sufficient to sort of handle. You can reduce all the other cases somewhat generically to this. The determinism you have to carefully get rid of. You have to carefully accommodate randomized non-interactive provers. But once you do that, it's not that hard to extend this to interactive protocols as well. And there the construction remains pretty much the same. What you're going to do is still the same. You're going to sample this x1 to xt, w1 to wt, and then take your actual x comma w, put it at a random location, and then just run the batch protocol on this instance that you have just constructed. Right? That's what the proof is always going. The protocol constructed is always going to look like. Completeness and soundness again follow very easily, and you can reduce the argument for witness indistinguishability to the non-interactive case, because given any protocol, really, given any interactive protocol that looks like this interactive protocol with these many messages A, B, and C, right? You can construct this other protocol where all the work is simulated by the prover P prime, and the prover P prime just tells the verifier what the view of the verifier was in its simulation. And you can show that these two protocols are equivalent as far as honest verifier witness indistinguishability is concerned, or at least honest verifier statistical witness indistinguishability is concerned. And the latter protocol, the P prime B prime protocol, is pretty much what we just analyzed. So it's much easier to show that it satisfies this honest verifier witness indistinguishability condition, and which then implies that the interactive protocol also satisfies this. Of course, this P prime B prime is not complete or sound. It's not sound, but this is only in the argument for witness indistinguishability. It's just part of the proof. You don't actually use the P prime B prime protocol. Right. So that's essentially the entire construction of the proof. I think there was another question, right? Was there another question?
No. So just someone dropped out. And thanks for the talk.
Okay. Wait, I'm not. All right. So let me very quickly wrap up the rest of it. I was going to say a little bit about instance compression, which is where the compression lemma I was talking about comes from. That's the context in which it was originally studied. And there, what you want to do is, here we were concerned about compressing the witness of an NP language, right? You have T instances, T witnesses. I want to give you a witness that is shorter than just putting all the T witnesses together. Instance compression deals with the same thing, but for instances, where you have T instances, and you want to take them and output a different instance that is a yes instance if and only if all of these instances are yes instances, right? That's the problem that they were dealing with instance compression, or more specifically the AND compression of a language. This is what it is. And there, a series of works by Portnow and Santhanam and Andrew Drucker showed that any language that has this kind of an the compressing reduction has to be contained in SDK with some caveats, actually the same caveats as that we have. And what we show similarly using similar techniques is that if a language has a batch proof, which again is sort of like saying I want to do this kind of AND compression, but for the witnesses, has satisfies statistical implies that L has an SWA protocol. Right? So that is parallel as that. There's not a coincidence because we use very similar techniques as well. But yeah, again, if you're interested in these things, these are other papers to look at, which do similar things as well. And finally, just a little bit about what happens when you relax the soundness condition to be this computational soundness rather than statistical soundness, the way I had defined, right? Meaning that you ask for soundness only against computationally bounded cheating provers, and there also you can the same techniques pretty much work. And there, what is known? Well, there we actually have constructions for all of NP, and we have had it for a while. And these constructions typically use some kind of collision-resistant hash functions. And they also have some other nice properties, but it is so far not really known what assumptions are necessary for these kinds of batch arguments. Like we know we have constructions for NP, but they use these collision-resistant hash functions. But do you need them, or can you construct them just from one-way functions? And there you can also draw some conclusions for some partial answers to these questions based on a similar approach. And there also what we show essentially comes down to the same thing, because the same transformation continues to work. And if you start with the batch argument, you can also similarly get an honest verifier SWA argument with the same caveats, where you have a non-uniform prover and inverse polynomial error. But in this case, if you additionally assume one-way functions, for example, you can actually get SDK arguments. So you can remove the honest verifier requirement, and you can also upgrade the kind of security you get to SDK from SWI without paying too much in the terms of the number of rounds even. Like you can just get a constant factor increase in the number of rounds, starting from the batch argument all the way to the SDK argument. And this is one interesting corollary of this is that is the following: is that because these SDK arguments for NP, so far we only know how to get them from the statistically hiding commitments. If you can somehow get batch arguments from one-way functions, this implies that you can also get SDK arguments from one-way functions for all of NP. Which is something we don't know how to do so far. So it'll be interesting either way. Like if you can show, for example, that you cannot get SDK arguments from one-way functions, then that would also imply you cannot get batch arguments from one-way functions. But if you are able to construct these batch arguments from one-way functions, then that will also be very interesting, because you'll have a new construction of these SDK arguments that we have not been able to improve on for a while. And then finally, we also have some interesting implications for non-interactive batch arguments, which are a stronger kind of batch argument, right? Because in addition to all the properties you already had, you're also restricting the prover to be non-interactive, meaning it just sends one message. And we also need to be more careful about what definition of soundness you have, but I'm not going to go into that right now. And for this also we have some constructions, but because these are stronger kinds of proof systems, we end up having to assume more. Whereas with the interactive batch arguments, you can do it generically from collision resistance. Here you need specific assumptions. We need LW, Bernoulli maps. We have multiple constructions, but they're all from stronger public key sort of assumptions. Right? And here also you can ask the same question, and again you can get some partial answers. And here this is what our transformations look like. Like our basic SWA transformation continues to work. But one interesting thing you can do here, because non-interactive arguments give you something more, right? You're starting with something stronger. So you can actually get something stronger as well. So it turns out that if you start with this non-interactive batch argument, first, as we saw in the first step of the proof, you can first get distributional witness indistinguishability. Remember, we only applied the min-max theorem after that step. So until that point, if you started with a proof system that had a uniform prover, you still have the uniform prover, as long as the distribution is sampleable and everything. And what you can do is, by using a series of transformations, you can actually get non-interactive, computational zero knowledge arguments, not statistical zero knowledge, but you can get this with uniform provers and negligible zero knowledge errors. meaning that you can end up with protocols that you can actually use. Because you have a uniform prover, which means you actually know what the prover is, and you have small enough errors, zero knowledge errors, that this could actually plausibly be used. So this could be seen, whereas so far we've only been thinking of whatever our conclusions were as attempts to answer as partial negative responses to questions of the form, okay, does this language have this kind of proof, right? This could also be seen in a positive way. This could be seen as one way to construct these kinds of non-interactive CSDK arguments, because they have uniform provers and negligible errors. You could possibly use them. Of course, if you look at our actual construction, there's a lot of laws, so you can't use things as they are. But actually, you know what? There's no real laws in terms of the protocol itself, because the protocol is, you just run the batch protocol. The only losses would be in the proof arguments, and that could possibly be improved. But yet another way to construct these non-interactive CSDK arguments from NP for NP. Yeah, so that's about it. I'll just leave this. So yeah, there are a bunch of questions that remain to be answered here. First of all, we started out trying to answer the question of, can all of NP have these proofs? And we reduced it to this question: does all of NP have SWA proofs? But we do not have good answers to this question, one way or the other. Right? And this motivates a study of these kinds of proof systems and the class of languages which have these proof systems in general, which we don't have so far. We have a lot of understanding of what the set of languages that have statistical zero knowledge proofs looks like, but for witness indistinguishability, we don't have anything as close. And that's partially because this is a less nice property to study. It doesn't have certain obvious closure properties that you would like, that make things convenient. It's not clear what a complete problem for this class would look like. There are lots of things that make it a little more difficult to study than zero knowledge, which is perhaps why we don't have an understanding of it so far. But it would be, at least for this purpose, at least for the motivation that we started with, it could be quite interesting. And the other is, in our general construction for batch proofs, we don't know how to remove the non-uniformity of the prover, or how to get negligible SWA error, because again, that's one thing we don't know how to do. We don't know how to take an SWA protocol and generically decrease its error, decrease its
Prashant,
WA.
Prashant, there is a question. So Shiva asks, are there similar results for batch PCP?
I don't know. I have not thought about this. What would it? So you want to construct one PCP kind of proof that can prove multiple instances? No, I don't know about this. Maybe you can. Maybe some of these arguments can translate there, but I'm not sure. I think you'll also have to there'll be multiple parameters, right? Whereas here we only have the length of size of the communication in the proof system. There you will have a couple of things. You'll have the proof length and the number of queries you are making. So you could try, if you have strong requirements on the proof length, then maybe you can get something very similar. Because okay, for one, the PCP proof is also an NP proof, right? So that will give you some. If you have very strong requirements on the PCP proof length, then that would have implications. Then the same implications would carry over. But if you don't have that, if you don't restrict the PCP proof length, but you do restrict the number of queries you are making, then I don't know. Then that's not obvious to me what you can say. Yeah, I don't have anything more to say about that. But that's an interesting question to ask.
It is.
Right. So this is another pair of questions that we have no idea how to approach. So with making the prover uniform, right? There are many uniform analogs of the min-max theorem, but all of them need something additional from the game that we have set up does not have. For example, one thing that all of them seem to need is, you need the payoff function in the game to be efficiently computable, which we cannot actually do, because in our case, the payoff function involves computing the statistical distance between two distributions on very large strings, right? Which we can't do efficiently. But maybe there's some way around it. Maybe if you set up a different game very carefully, you can do it. Not sure. And the negligible SWA errors as well. So unlike with SEK, with SWA, we don't know how to generically make the errors smaller. Which I think we also don't know with non-interactive SDK, but here also we don't know how to do that. So So that's another thing to figure out, whether you can do it generically, or if you cannot, can you modify the construction to make the error smaller anyway? And neither of these we know how to do. And then there's the larger questions of the slightly different but still larger questions of that ask specifically about certain kinds of batch proofs. So I told you that all languages in UP have batch proofs, right? But the constructions of these batch proofs are inherently non-interactive. Interactive. If you can try to make them non-interactive using standard collapse, the round collapse arguments from interactive proofs, but if you do that, you end up with something trivial. So for non-interactive batch proofs, we still don't have any non-trivial constructions. Again, maybe for some very specific structured languages, you can get it, but we don't have good constructions for generic classes or languages with generic properties. Even with unbounded provers, it turns out, like in the UP case I was talking about earlier, the prover is actually efficient given the witness. But here, with unbounded provers, we still don't know how to get these non-interactive batch proofs. And finally, there's always a broader question of we have batch proofs for UP, can you get it for anything outside UP? We still don't know this, right? As I was saying in the beginning. These are a few questions, few interesting directions surrounding this work that we don't know answers to. And you can look at the paper. I think we have a longer list of related questions in the paper. So if you're interested, you can look at that. But that's about it. That's all I had to talk about. I'm happy to answer questions. And also, if you're interested in this and you want references or anything, feel free to email me. I'll find something. You can find something. If you have any questions now, I can answer them as well.
Yeah. Anyone? Any questions? Okay. So maybe I'll ask one. So 3. So like, are there no lower bounds here? Sounds like this should not exist.
Yeah,
non-interactive.
I don't know anything better. I mean, you still have whatever we are saying here, you still have, but that's still only up to SWA, right? One would hope that maybe you can derive stronger properties than just SWA from these things, but we don't know how to do that.
Okay, I see. Yeah. If there are no other questions, yeah, we can thank Prashant for the talk.
Okay, thank you. Thank you for having me.
Yeah.
I'm going to stop sharing.
Yeah, and thanks for agreeing to give the talk. It was very nice.
Yeah, of course. What other talks do you have lined up?
So last week we had Pratay. He gave a talk on VRFs. And I think we have a couple of more speakers, but I don't think they're confirmed. They're scheduled yet.
Okay. Okay. Thanks again for having me. And I'll see some of you later this year, hopefully.
Yeah. See you. Thanks.
Bye.